So just like when we talked about limits of functions, if we were to apply the definition of the derivative in order to compute the derivative of every function, it would be very difficult in general because some manipulations would be really hard, and that's why we have this some algebraic properties that allow us to manipulate derivatives and use some techniques to compute the derivative, to more easily compute the derivatives of some functions. Okay, and these are these five. Okay, so the derivative of the combination of a function, of linear combinations of functions, is the linear combination of the derivatives, and this goes from the linearity of the limits. The product rule, so the derivative of the product is the derivative of the first function times the second function plus the derivative of the second function times the first function. Now the chain rule, which is the derivative of the composition of two functions, is the derivative of the first function composed with the second times the derivative of the second function. The derivative of the quotient is this rule, f prime g prime minus f g prime divided by g squared, and then the derivative of the inverse function is 1 over the derivative of f, but evaluated at the inverse of the point. Okay, and then we're going to go over the proof for the five properties so that you get a sense of them. Right. So the first one is goes straight from the linearity of the limits. Okay, so we want to evaluate the derivative of this function lambda f plus mu g, where lambda and mu are real numbers at a point A. Okay, and then this, applying the definition, this is the limit when x goes to A of lambda fx plus mu gx minus, and then lambda fa minus mu ga, right? All of this divided by x minus a. But then you can see, it's easy to see that you can separate the parts related to f and the parts related to g, right? So then we have the limit when x goes to a of fx minus fa, and then we have a common factor lambda, we can take it out, divided by x minus a, and then the same thing, minus mu limit when x goes to a of gx minus ga divided by x minus a, right? Now this thing here is the derivative of f at a, and the second fraction, this limit here, is the derivative of g at a, right? So we can say that this is, well, we can write it like this. Minus mu, sorry, this is minus, so it's plus mu g prime at a, okay? So the same thing. Okay? Now the others are right like this, okay? This demonstration, these proofs are all very similar, right? It's just applying the definition of the derivative and then do some algebraic manipulations. Okay, the derivative of this function f times g at a is just the limit when x goes to a of fx times gx minus fa ga, right, divided by x minus a. Now I want to get a factor f prime here, so what I want is to introduce this this new term minus fa gx, right? Because if we have that, now we can take a common factor gx, and then this is fx minus fa divided by x minus a, this is f prime, right? And then we can say, well, but if I've summed this, so I subtracted this, so I have to sum it again, so then I have f of a gx minus f of a ga, right? divided by x minus a. Okay, this is plus. Okay, we're just adding and subtracting the same term, and this is the same thing, separating the fraction in two, right? Now, the first limit, we take a common factor gx, but the limit, so we can write it like this, right? The limit when x goes to a of gx times the limit when x goes to a of fx minus fa divided by x minus a, and then we have plus, then we have fa out, and then the limit when x goes to a of gx minus ga divided by x minus a. So this is g at a, f prime at a, right, plus f at a, g prime at a, okay, which is what we wanted to prove, right? So let's go for the chain rule, which is a very interesting one. The chain rule. We have the derivative of f composed with g at a, which is actually this is the limit when x goes to a of f of gx, right, minus f of ga, that's what the composition means, divided by x minus a, right? But then you see that there's a gx, ga. If we had a gx and ga in the denominator, we could write this as the derivative of f at g, right? So let me multiply and divide by gx minus ga, right? So this is f at gx minus f at ga divided by g at x minus g at a times, and then we have g at x minus g at a divided by x minus a, right? Now this thing, the limit of this thing is going to be, let me write it like this, x minus a, g at x minus g at a divided by x minus a. Okay, this is going to be g prime. Okay, and then we have the limit, and let me rewrite this. Okay, when x goes to a, then we can have that y goes to, we can call it g of x, let's call it y, right? Let's call this y is equal to g of x, right? When x goes to a, y goes to g of a, right? So then we have f at y minus f at g of a divided by y minus g of a, right? So now this thing, as I said, is the derivative of g at a. And now this is the derivative of f, but at g of a, right? So in other words, this is f composed with g, right, times g prime, all of this at a, okay, which is what we wanted to prove here. Okay, let's go for the fourth quotient rule. The quotient rule says, so we have f divided by g prime, right? So we can think of this as f times 1 over g prime, right? And then apply the product rule, right? This is f prime divided by g plus f times 1 over g prime, okay? But the question now is, what is 1 over g prime, right? What is this? Now 1 over g is, if we write this function phi of x is 1 over x, right? Then 1 over g is phi at g, right? So the derivative of 1 over g is going to be, sorry, this is not this is phi composed with g. So the derivative of this is going to be, applying the chain rule, is going to be phi prime evaluated at g times g prime. Okay, so what's this, the derivative of this? Okay, let's see, what's the derivative of 1 over x prime? So this is the limit when x goes to a, or let me in this case, let me write it like this. When h goes to 0 of 1 over x plus h minus 1 over x divided by h, then we take everything in the same fraction, so we have x times x plus h, right? And then we have x minus h, all of this divided by h, right? X and x cancel out, so then we have the limit when h goes to 0 of minus h divided by x times h times x plus h, right? H and h cancel out. The limit when h goes to 0 of this is 0, so then we have x times x squared minus 1 over x squared, which some of you already know, right? So then we can write this like this. This is f prime divided by g plus f, and then the derivative of 1 over g prime is phi, which is the derivative of 1 over x, which is minus 1 over x squared, composed with g, so this is 1 minus 1 over g squared times g prime. Okay, and so this is f prime over g minus f times g prime over g squared. If we want to take everything in the same denominator, we have g squared, and then we have f prime g minus f g prime, which is what we wanted to prove. Okay, obviously provided the g is different from 0. Okay, and then the final property is that the derivative of the inverse is 1 over the derivative of f at f minus 1. Okay, well, in order to prove this, well, we're going to use this property of this of the inverse, right, which is that f composed with f minus 1 at x is going to be x, right? Now we differentiate both sides. The derivative of x is 1, as we know, so this is going to be this, and but in order to compute this, we need to apply the chain rule, right? So this is f prime composed with f minus 1, right, times f minus 1 prime at x equal to 1. Now if we solve for this, this is f minus 1 prime is going to be 1 divided at x, okay? It's going to be 1 divided by f prime composed with f minus 1, okay? So it's like f prime evaluated at the inverse of that point, okay?